We're discussing about noise, input referred noise, and noise models of basically characterizing any two-port network with a voltage and a current source at the input, right? The input referred noise, and where did we were essentially saying that. Let me just go back to one lecture. Yeah. So this is where we had stopped, where we had modeled the two-port noise, input referred the two-port noise, and then we were trying to see that under what condition this two-port noise, this voltage and the current source, one of the voltage and the current source can be neglected, and then we saw that if the source impedance is zero, that is, you are driving your two-port network with you're driving your amplifier, for example, in this case, with a ideal voltage source, right? So then the input referred current noise, IN ref, will get shunted through that source, and it will not be necessary. You can as well model the entire noise with V in ref. And alternatively, if you are driving with a current source, right? So then this V in ref doesn't have any use because it doesn't it doesn't contribute to the model. Only I in ref contributes to the model, and we can essentially model the entire noise with the input referred noise current. And again, just to remind you, these are model noise sources. These are not actual noise sources, right? So there is no actual noise. You cannot measure these input referred noises by putting any voltmeter or an ammeter. Everything that has to be measured has to be measured at the output, right? So these are only mathematical models. Okay. So let's start off with from where we left off. But we have been. I'll put another feature to this. That is something that we have not talked about in detail, but it should be obvious by now. Till now, we have been considering cases with only there is no frequency dependence in the transfer function, and what happens to the noise, right? So if there is a frequency dependent transfer function, which obviously there will be, right? You have filters, you have so many in RF chains, you want to pass some signal, you do not want to pass some signal, which means there is a frequency dependence. And if that is the case, how do we go about modeling noise? For example, again, let's take a trivial example. Let's say this block, this two-port network, has a transfer function of A, voltage transfer function of A, and you have a voltage noise at the input, right? You have a voltage noise at the input, which is modeled with a noise source Vn, which has a power spectral density of, let's say, 4 kTr. 4 kTr is the power spectral density. Now again, so what will be the output noise? Right, power spectral density times A square, right? So again, if you've forgotten about it, how do you go about doing it? Treat this noise source just like a signal source, right? So at the output, if Vn was a signal, at the output you would have gotten Vn times A, but Vn times A, when gets dealing with the noise, doesn't make any sense. We have to talk about powers, noise powers, so essentially I square Vn, so it becomes Vn squared times A squared, right? And the power, since Vn is not a deterministic source, it's not a sinusoidal source, right? It's a noise source. We talk about it power spectral density. So the output becomes power spectral density times A squared, right? So the output becomes 4 kTr times A squared. Okay. So here A is considered to be noise to be constant across all frequencies, right? But let's say A is not constant across all frequencies, and it has I call this h of f. Right? The same case, what will the output be, and how do you go about thinking about it?
Just pure multiplication of those frequencies, input of the input and h of f.
Right. So in frequency domain, it will be just input and out h of f. So similarly, I mean, whatever that same logic that I used just a minute back, if you go about finding out, assuming Vn is a signal, the output would have been frequency domain component of Vn, that is Vn of f times h of f, right? But this is not a signal, so you go Vnf squared, whatever it is, times h of f squared, right? But there is slight amount of catch there, right? So the catch is h of f has a phase response as well, right? H of f is not only amplitude, it has both magnitude and phase, right? But noise does not have any phase information. Why? Because what does phase essentially tell you? In principle, what does phase tell you? What is meant by phase? Pardon? Polarity, okay. Not necessarily polarity. If you are 180° out of phase, you say it's opposite polarity. But in general, why is phase necessary? That's an application of phase. Okay. So I'm just basically asking you, let's say I say the transfer function h of f is some one angle 20°.
Put a sinusoid at the input and shift the phase.
Yeah, it will basically it's a delay. Right? Phase equivalent to a delay to a sinusoid. Right? So when I say the phase is frequency dependent, it essentially means that at certain frequency it gives so much delay, in another frequency it gives a different delay. Right? That's all it means, right? Phase gives you delay. Now, when you are dealing with noise, does it make, I mean, will it make any difference if you observe a signal now or you observe a signal after a delayed version of it? Rather, let me just, let me correct myself. When you're dealing with noise, will it make any difference if you observe the noise output now or you observe the noise output after some time? When I say any difference, I mean difference in the perspective density of the noise. You will not get, right? Because totally uncorrelated stuff, right? So which essentially means that phase information is not there when you are observing noise. Because ultimately what you are doing, in a way, you are thinking that you are observing it at a certain instant of time and doing multiple experiments and adding the power of all the experiments together, right? We are, inherently in that averaging, getting rid of that phase information, because whatever you are doing, the experiment that you are doing now and the experiment you are doing after this, there is no correlation between the data. You have it here or there. Right. So that is a very, very hand wavy but intuitive way of thinking about why phase is not necessary in noise calculation, or rather in the perspective density, there is no information of phase. I should not say phase is not necessary. If things go and cancel each other, then obviously there can be phase can be necessary. But in perspective density information, no phase information is present. Okay. So in other words, what I'm saying is here you have your output is 4 KTR times mod of h of f squared. Okay. So this will be necessary later on, right? So when we deal with perspective density for filters, for example, you should be this will be helpful. The another part question, right? So another part that is also important is, so let's say I have a spectrum analyzer. A spectrum analyzer is basically a device, is a measurement equipment where you see the strength of the signals in frequency domain. In the first class, I showed you a demo. So that was essentially a spectrum analyzer, right? So you don't see across time, you see across frequency. Okay. So let's say I have a sinusoid. and there is some noise also. Let's say there is some noise. So I have a resistor which contributes to noise, and you have a spectrum analyzer. You have a big screen, and in the screen you see some wiggling here and something sticking out. Okay, so if this sinusoid is at a frequency f0, then the sticking out that you are going to see will be at f0, right? So the question. So the height of whatever that is sticking out, right? So the measurement that you are going to read here will be equivalent to the power contained in that input sinusoid, right? But what about this wiggling here? This small wiggling that you see across that fills up the bottom of the screen, that essentially is the noise. Okay, so this is noise. But so now there is an important distinction to be made. The power of a sinusoid is not frequency dependent, right? Power of a sinusoid is a value which is equal to Vp squared by 2, right? But what about the noise? Noise gives you, so now when I say whatever this red stuff is noise, you should ask me, is this noise path spectral density or total noise? Now, before I explain that, let me ask you, is there a difference between path spectral density and total noise? Right. So path spectral density is a noise in 1 Hz bandwidth, right? If your bandwidth is 10 Hz, you'll have to integrate over 10 Hz. If your bandwidth is 1 kilohertz, you have to integrate over 1 kilohertz and so on. So in one of the earlier classes, we saw that if you have a very wide bandwidth channel, you are going to accumulate a lot of noise because effectively it gets multiplied by the bandwidth, right? So this is whatever you are seeing here is noise PSD, but total noise is whatever is V or Sn integration of Sn or df over the channel, right? So let me just say over bandwidth. Okay, but again, I am harping on the same thing again. The height of this guy does not depend on bandwidth, because that's a tone. That's ideally that's a delta direct function, right? So why is this important? It is important because if you reduce the channel bandwidth, you are going to reduce the noise, but you are not going to affect the signal if your signal is a sinusoid. Okay, so that is one way of increasing signal to noise ratio. Okay, so that is sometimes done in case of, so what is the trade-off? If you let's say reduce the bandwidth, intuitively, what do you think is happening? Pardon? Yeah, something about time you said, yeah.
Time period, we are allowing more time window for that to happen.
Yeah, okay. So let me rephrase the question. So in terms of communication, when you are communicating something, you would like to communicate with as less a time as possible, right? Which means you need high speed, you want low noise, you want low power, and so on, right? So in terms of all these parameters, if you reduce the bandwidth, what gets affected? Obviously, noise gets affected, it reduces. What other thing gets affected? Speed gets affected. Naturally, bandwidth has a direct trade-off with speed, right? So there is a direct trade-off between how fast your communication can be with respect to how noisy it is, right? So when you are trying to send out information from a very noisy channel, or you expect the signal that is arriving to you will have very low strength, and there is nothing you can do about that strength, then it's better to have a very narrow channel. Signal will eventually arrive, but it will arrive. you'll be able to distinguish. Right? That is why some of the space applications have the data comes at a very low rate, right? So they don't just come like Netflix videos. Okay, so they eventually come, but you have to do some processing on top of that also, but they come at a slow rate to reduce noise. Yes.
Bandwidth, the signal that we'll be getting won't be just a tone, it will be a complete range of frequencies, right?
Yes.
So the bandwidth that we are talking about is that range.
Is that range? It will not be a tone, but if let's say you are around 500 megahertz, and we say that I am taking out 1 kilohertz around 500 megahertz, that's equivalent to a tone. For all practical purposes, that is equivalent to a tone. Yeah. Yes. Right. So that's what that SAW filter was also doing in our receiver to some extent. But application was different. It was where basically the way we introduced SAW filter was to cut off the blockers, right? The SAW filter also does this job of cutting off out of band noise. Right? So anything that comes out of band also reduces the signal to noise ratio. So it's better to shut them out as soon as possible.
So it will like double the bandwidth. If we go from 1 kilohertz to 2 kilohertz, so the capacity doubles, like we are
Yes.
able to transmit at 20.
Yeah. So Shannon's,
Signal to noise ratio, signal to noise ratio 58.
if you do not increase, if let's say you do not want to open up the channel, and you open up the channel and you do not use the full channel to send your signal, right? Then obviously your signal to noise ratio decreases. But let's say you say that I open up the channel and I use the entire channel to send the same signal multiple times through. Let's say I say my signal bandwidth is 1 kilohertz, but I have opened up 1 megahertz channel, right? So, and if I say I send a tone of only 1 kilohertz and I do not do anything to the rest of the 1 megahertz, so I'm inviting noise from that 1 megahertz channel, but my signal is only at some tone around 1 kilohertz. So that obviously is not a good thing. So if possible, then you don't have anything else to send, then you can as well say that instead of sending only 1 kilohertz tone at one particular frequency, I will send 1 kilohertz tones at multiple frequencies. So that way, basically, I mean, boosting the from the transmitter end, I'm boosting the signal.
Are we transmitting the same signal power?
You can. So if that is the only option that we, yes. So I am basically taking the example of a space application. If your satellite is somewhere in the outer space and you know that you are going to get a very small signal strength, then it is better to have redundancy in signal, right? So that is what this is one kind of redundancy. You can do that. Alternatively, you can say that I do not want to, because satellites are also power sensitive in the sense that you do not want to spend too much power transmitting signals from a satellite. So moment you say that I want to send more power, which means the power efficiency there goes for a toss. Alternatively, you can say that whatever I am able to send, I will send in that limited bandwidth. At the base station, I will put a very sharp filter within that 1 kilohertz only. I will not have any redundancy, and my signal to noise ratio will be decent, right? So this, if you remember, for those of you who also might have also taken digital communication courses, this essentially is Shannon's channel capacity theorem. It directly is the consequence of that.
Trade-offs it shows between having huge bandwidth and the SNR comes down because
Yeah.
we are already large.
Yeah. So again, SNR comes down if you have bigger bandwidth than necessary. That necessary part is important thing, right? If you are using the entire bandwidth to send signal also, then SNR doesn't really come down.
Multiple tones, then SNR can also do.
Yeah. So that was other example that I gave. So basically, moment you open up channel, it's inviting noise, right? So if you are okay with that noise because you also have enough signal strength, you are good. If you are not okay with that, just reduce the bandwidth. It will be slower, but you will get something, right? Okay, fine. So I will take a detour from here in terms of dealing with noise like this, and go back to the previous class, wherever we ended, and we'll talk about one example of how to do an input referred noise, and then come back to this at the back end of this class. Okay, so I'll take a detour. Yes.
So the spectrum analyzer doesn't have any noise sources of its own. Like it doesn't contribute.
Everything will have a noise source. Just that a good spectrum analyzer will have a better way of suppressing noise. It will not contribute too much of noise on its own than a poorer spectrum analyzer. So essentially, what do you characterize? How do you characterize a good noise spectrum analyzer or not? You basically check the noise floor, right? Per unit bandwidth, how much noise it gives on its own when nothing is connected, right? So if it already gives more than what your signal you are receiving, then there's no use. So that's the difference between a good spectrum analyzer and a bad spectrum analyzer, or not so good one. So I'm going back to the two-port input referred noise model, because in the last class I told that I'll show you with an example. So let's close this, and I'll come back to dealing with noise in a system level after that. So let's say I take a trivial example of maybe a common gate amplifier where this is incrementally shorted, and this is my two-port. Right, so you are giving this to the customer, and your customer wants what is the equivalent model, noise model looking into here, right? So input referred noise model, that you will get. Okay, so how do I go about doing it? So I know that my input referred noise model is equivalent to this, Vn In and some Rin. Right? So Rin is the input impedance, Vn and In are the input referred noise voltages and currents. Okay. So let me call this one R1, let me call this one GM. When I call GM, obviously I mean that we are referring to the transconductance of the device. So how should I go about finding out these input referred noise? Note that they don't exist in principle. This is a model. So what is the algorithm? How do I figure out what will be the input referred noise? Yeah, so I also need to note what is the output, right? Without output, I cannot refer anything to the input, the referred thing. So let's say I say that the output is the output can be more current or voltage. So let's say I'm interested in output current, incremental output current, right? So which means this is incrementally shorted. I am interested in I out. Okay. So then I need to figure out. So now if this transistor and resistors are noisy, I need to figure out in the presence of noise and no signal, what is the output noise current that I am going to get, and then find out a way of manipulating the noise model in such a way that I get the equivalent Vn and In for that amount of noise, right? So step one is finding out the total output noise current. Okay, so help me with this. So what should I do to find out the total output noise? Right, so basically we introduce noise models for transistor and the resistor. I mean, for the resistor, I can as well put voltage or current. Since we are doing current, I put current. So what do I do to the input? Yeah, but yeah, correct, right? So which is true. In one case, we can treat it as a open, and another case I can treat it as a short, and whatever we get, right? So now tell me which one, what should I do? Let's say I want to find out Vn, right? I want to find out Vn. Then what should I do to find out Vn? Short the input, right? So I will short the input. So basically, I short the input, then all the incremental noise from the model is going to go into the short, and it's not going to induce anything at Rin, which means its contribution at the output. Whatever I get under this condition at the output is for the input referred voltage noise. Okay. So I will short the input. So I'll simply short the input. Right? And I'm going to find out this IN out. Okay. So let me also name them. So let's call this IN1, call this IN2. So what will be IN out? Let's do the easy one first. Will IN2 come out to IN out? Yeah, so IN2 will not come out because ultimately it will go through the short. Right? So that goes in the expression, that will not appear in the expression. So that's good. So we'll have to deal with IN1. Right? So what will be IN1 contribution to the output? How will you go? I mean, obviously you have to replace with a small signal model, but I assume now you are comfortable with small signal models. Without replacing, you'll be able to do. So how do I go about figuring it out? Pardon? Yeah, IN2 basically doesn't come into picture at all because IN2 gets shorted. So I'll remove IN2, right? So IN2 is not there. So then only contribution of IN1 will be there. So what will that contribution be? So IN1, so basically it will be IN out then. Yeah, so basically entire IN1 will go into IN out. Correct. So this is basically IN1. Okay. So what will be SVN out then? Same as SVN1, IN1, or rather SIN. This is not V, this is the current. So SIN1, which is 4KT gamma GM. Right? Fine. So which essentially means that now how do I figure out what is the cross spectral density of Vn from this? So I got IN out. Why should I simply divide? What is the method? How are you going to, let's say in this case it's probably simpler, but in general, what are you going to do? Yeah, right. So essentially, what I am saying is, this is equivalent to saying that I have another model where the elements inside this two port are noiseless, right? So no noise here, but all the elements are present. And the equivalent noise source is Vn at the input. Sorry, not here. This is not the input. And what is the effective current? And this should be equal to the noise current that I found out in the previous step, right? So what will be IN out? in this case, in terms of Vn? Gm times Vn, right? So gate is grounded, source is excited with Vn. So the amount of current that is pushed upwards is Gm times Vn. So this becomes Gm times Vn. So so this power spectral density of this should be equal to this, correct? So what will be the power spectral density of SVN? It will be 4 kT gamma Gm divided by Gm squared. But why Gm squared? Because we're talking about power, so IN out squared, right? So which is equal to 4 kT gamma over Gm. So this is SVN. So we got SVN. We also need, so we got this guy. We need IN also.
Sir?
Yes.
Then we are neglecting R not using the approximation Gm R not.
Yeah. We are neglecting R naught. Yeah, that's the subtext. Yeah, if you put in R naught, method remains the same, it will be slightly more different. Expression should be slightly more different. But that's a good point. So now I want to find out what is the effect of how do I model IN? What should I do? In the previous case, I shorted. Here I will open, right? So again, let's do. So to find. So this will be opened. Now I'm going to find out. The total output noise again. Fine. So tell me, what should I do? Let's consider the case for the noise of R2. How much will R2 come out? How will I go about figuring out what will the contribution of IN2 in IN out? Right. So yeah, we'll come to IN1. Right? So let's do IN2 first. Yeah, right, correct. So what Harish is pointing out is that we can do superposition, right? So mentally we assume that IN1 is not present when obviously you can have another schematic and remove it off, but I presume that you are comfortable with doing that in your mind at this stage. So if you assume that IN1 is not there, so IN2 essentially comes to this node and it can go up, it can go down, a decision to make. What fraction will go up is basically the ratio of the conductances, right? Conductance division, right? So IN out will be this IN2 times GM by GM plus G2, right? For this is the contribution of IN2. What will be the contribution of IN1? The same thing. So yeah, tell me. So IN1 comes, let's say I again come to this junction. IN1 comes here. One part goes this side, one part goes down. The one that is going up will contribute to IN out, or one that is going down will contribute to IN out. Okay, so let's come here. This guy goes up. Will it go to IN out or will it circle back in? Yeah, so that part that goes out, that is coming down, right? So this guy comes this way, right? So essentially the part that is going down is the one that is contributing to IN out. Okay. So what part is going down? Again, IN1 times G2 by GM plus G2. Okay. Okay. So what will be SVS or rather SIN out in this configuration? It will be IN2 is 4 KT by R2, which is G2, times GM by GM plus G2 whole squared, plus IN1 is 4 KT gamma GM times G2 by M plus G2 whole square, right? So this is SN out, but now I mean, whole purpose is to figure out what is the input referred noise in terms of noise current. So I'll have to go back to the model and then again null all the current sources inside the box. And I assume that there is this IN that flows here. And I will find out IN out in terms of IN and equate it, right? So what will be this IN out in terms of IN? Again, the part of IN that goes up, right? From that node is the one that I'm interested in, that is contributing to IN out. So in this case, IN out is IN times GM by GM plus G2, which means that SIN out is 4K, or rather SIN times GM by GM plus G2 whole squared, and then you do the algebra, then you get whatever you get. Okay. Make sense? Let me also complete this. Okay. So now you might ask that why should I bother with all this pain? Because ultimately the noise is at the output, right? It seems like calculating output noise is easier than calculating input noise. Because output noise, I am doing only one step and I'm finding out the total output noise. To find out the input referred, it looks like I have to do so many steps, right? I find out the one's output noise, then short the input, then find something, open the input and find something, and then do all sorts of juggling and then come up with something. And that whatever we come up with is also seems to be a big expression. So other than maths, what is the usefulness of this, right? So that is a natural question that should arise in your mind. So the next part of the lecture is essentially to motivate why is it essential? Okay. Before I go there, any questions so far? Okay. So let me now go back to the system level descriptions once again, right? So this was a circuit level example. We started the class off with a system level description, and then I took a break. Now I'm going back to the system level description again. So let's say I have a system. I have a 2-port where the input you have some noise and some signal. Okay. If I have to ask you, find out the signal to noise ratio of the input What are you going to do? What steps are you going to do? So you want to find out the signal to noise ratio of the input. You have a spectrum analyzer, you found this, right? This is, let's say, the picture of a spectrum analyzer. How would you know what is the signal to noise ratio of the input? Firstly, let's go with the signal. How do you know what is the signal strength? Yeah, the tone that is standing up, the power of that, you just read it off, whatever you get, right? So the strength of this is signal. This is signal. Or if I just say the power is P in. So it will typically give you readings in terms of dBm. So whatever dBm you get, right? What about noise? How do you know what is the noise strength? Yeah, noise floor times bandwidth, right? So whatever you get here, so this typically is in dBm. This guy is in dBm per hertz, because this is power spectral density, right? Power per hertz, power you can express in dBm divided by hertz. So essentially you then say that my bandwidth of interest is probably this much. So your signal to noise ratio is then SNR in is P in divided by whatever noise PSD that you are getting, N in times the bandwidth. Right? Make sense? So when expressed in dB, this essentially becomes, so SNR in dB becomes P in dBm minus N in dBm minus 10 log bandwidth. Okay. So by the way, I can club dB and dBm together in this. You're comfortable with that? So this is dB, these are dBm. Right? So why am I able to do that? Because it's basically a ratio. And as long as the units are in the same, I mean, I'm not clubbing dBm and dBw together, or dBm or dBv together. Right? So as long as I don't do that, this is acceptable. Okay. Fine. So now I pass it through the two port. I'm going to, let's say the two port has a nominal gain of G. Right. So this is another thing about RF. G is typically referred to as the power gain, and sometimes obviously it is also a conductance. Right. So be careful of which G we are referring to at each time. So G in this case means power gain. Okay. When I say power, which means there is associated resistance somewhere, right? So the input resistance is basically the source resistance of whatever is coming in. While output is whatever is the output you are driving. If there is no output resistance, but the output is a capacitor, right? There is no power associated with that. In that cases, we just simply take the voltage and square it. Right. So that's the typical assumption. So G is now the power gain. So what would you expect the output to be? So let's start with the signal. What would you expect the signal output to be? Some tone of height G times P in, right? So essentially, if I write everything in dBm, this becomes P in plus G in dBm, right? What about the noise? What would we expect the noise to be? By the noise will also increase by a factor of G. So this is, I should say N in plus G, right? But will it, in a real two port, will it only increase by this amount or will it increase by more? Assume that it's a generic noisy system. Right? This is a two port which has noisy elements inside. So in general, will it increase by, so basically what is the SNR out?
Plus if we consider that source as noiseless, then it could be like this.
No, what I meant is the block, the two port is noisy. Two port will have noisy element. It will have, so basically I will have some extra, let's say NM. Right? If that is an amplifier, I'll have NM. So your SNR, signal to noise ratio at the output, has increased or decreased with respect to the input. It has decreased, right? So you have added more noise while processing the signal, right? The best case is you cannot add, you don't add any noise. You cannot take out noise because it is anyway within the signal band. But the best case that you can do is you do not add any noise, right? But if you add noise, how much degradation of the signal to noise ratio you have incurred is obviously a matter of importance, because anyway you are trying to process very low noise and low SNR signals. So that has a name, technical name, it's called noise factor. Okay, so noise factor, or F, is essentially SNR in over SNR out. Right? This is in linear scale, right? So these are in linear scale, not dB. If you take dB, then it's called noise figure. One second. Huh? Yes.
It shouldn't be like P in dBm plus G in dB.
Ah, yeah, should be dB. dB. Thank you. It's okay. So yeah, fine. So I hope that you are convinced that this noise factor or noise figure is an important metric, right? So if you are, and what does it imply? What does it characterize? It essentially is characterizing your system that you have built, your amplifier that you have built to, you are trying to basically figure out how good or bad your amplifier is with respect to degrading the SNR. Okay. So noise figure of 0 dB would mean, what would it mean? A noise figure of 0 dB? Your block doesn't contribute to any noise, right? If your SNR, if your noise figure is 3 dB, what would it mean? Three dB means F is 2, right? F is 2 means SNR out is half of that of SNR in, which means how much noise does your block contribute?
3 times any.
With respect to the input noise, how much does it contribute? Your SNR has basically degraded by a factor of 2. And if you think it with respect to the input, degrading by a factor of 2 means noise increased by a factor of 2, right? So your block has essentially added exactly the same amount of noise that was coming in. So whatever was coming in, on top of that, it has added same amount of noise, right? So it's a noise figure of 3 dB implies that. And that will also be evident shortly from the expressions. So let's break this expression down. So your noise factor is essentially, now SNR in is P in over N in by P out over N out, which is P in over P out times N out over N in. Your P in over P out is essentially 1 over G by definition. And your N out is essentially whatever N in was coming in multiplied by G plus the noise contributed by the amp, right? So this is N amp by N in. Right? So I will write it slightly differently. I will take this G in. So what is the denominator? I can basically say that denominator, this is output noise if the amp is noiseless. Right? Does it make sense? So if the amp is noiseless, your output would have been, the output noise would have been N in plus G, right? Or N in times G in linear scale, right? So N in times G times N in is basically output noise if the amp is noiseless. And what is the numerator? This is the output noise in the presence of, or output noise in the real amp. Okay. So this is another, I mean, often you will see that there are multiple definitions of noise figure or noise factor that are used in the literature. Classic one is SNR in by SNR out. Another one is this, right? Output noise in the presence of total output noise divided by the output noise if the amp were noiseless. Okay, so each of them have some, there are some places where you would find one of them more useful than the other. So let's stick to this for the time being. So F essentially then becomes 1 plus N amp by G times N in. Okay. So very often, if you pick up any RF amplifier that you find in the market, you are going to see two very important specifications. One will be gain. There are many specifications, but you are definitely going to see gain, and you are going to see noise figure. So if you pick up, I mean, after today's class, go to any of the websites where you can get electronic components and search for an LNA. You are going to see the gain and the noise figure are paramount. They are going to be present. Nobody is going to give you N amp. They are going to give you noise figure. Okay. So if noise figure is given to you, how do you figure out what is N amp? It's straightforward from here. So your N amp becomes G times N in times F minus 1. Right? And if I now refer it back to the input, assuming, so essentially now what I'm saying is, this is your N amp, where I have connected it like this, and this is the N out, right? So your N out, so if your N in is given to you, what is N out? By definition of noise factor, what is N out? So noise factor is output noise of the real amp divided by the output noise if the amp were noiseless, right? So, and let's say F is given. I want to find out the numerator. What should I do? I simply multiply it with the gain and the noise, right? So N out is essentially F times N in times G, right? So now N amp, if N amp is given to you like this, and I want to refer everything back to the input in this model, and I would like to see that this is N amp input referred. Your N in is coming here. Your output will be whatever it is. Then what will this N amp be? Note that in this case, N amp is this, and I am referring back it to the input, and there is no other noise source anywhere. Then what should I do? Simply divide it by the power gain. The G is a power gain, the square is embedded inside. Okay, so essentially your noise factor becomes, or rather your input referred noise becomes, in terms of noise factor, N in times F minus 1. Okay. So this is basically, I mean, once you understand the first picture, everything is deduced from there. But the reason we are going through this is because, firstly, all data sheets of all RF components are measured with respect to noise figure, right? Nobody will give you exact noise in terms of dBm per hertz. It will be with respect to noise figure, and there's good reason for that. The main reason for that is it is always assumed that your input is a 50 ohm load that comes from the antenna, and everything is matched to 50 ohm, which means the input noise is fixed at 4 kTr times 50. It is standardized, right? So if the input noise is 4 kTr times 50, it makes sense to characterize everything with respect to the noise of a 50 ohm load. Then I already know I do not have to back calculate this and that. And that standardizing with respect to a signal to noise ratio of an input or the noise contribution of the input is essentially what noise factor does, or noise figure does. So that's what we are doing. So in principle, if something is, if let's say I have a amp, unilateral amp, which has a gain G1 and a noise factor F1, one of the first things that you should ask yourself now is, what is this noise factor referred to? Because unless you know N in, you will not be able to know what is the contribution of the noise of the amplifier. Because by definition, noise factor is with respect to an input SNR or input noise, right? So again, there is a weird thing that can trigger people off if you are not careful. Is what is the noise factor if N in is 0? If input source is noiseless? Infinity, right? That is weird because I cannot work with infinity, right? But why? What is the intuition behind why it is infinity?
That also contribute will be F times N.
Right.
So one is going to 0, other one has to go to infinity. So that
right. So yeah, exactly. Right. So it's essentially SNR in over SNR out. If input is 0 noisy, but you have signal, which means by definition your SNR in is infinite. Right. So one moment you have something as infinite, and your block will obviously add some noise. It will never have 0 noise. It will add some noise, which means you have finite SNR at the output. Input infinite SNR, finite SNR output ratio will become infinite, right? So this noise factor definitions breaks down when you do not consider input noise, but that never is the case. Especially in RF system, you always have a 50 ohm noise at the input, so you don't have to bother about that. But the part that you need to convince yourself now is F1 or if noise factor is with respect to a standardized input source. This is not by definition, it is not with respect to the whatever the block that it is being driven by. Right? Noise factor with respect to, so it's standardized input source, not with respect to the input source it is being a particular block is driven by. Right? So now with that definition in mind, so let's say you have another amp which has a gain of G2 and noise factor of F2. I want to figure out what will be the noise factor of this entire system put together. Right? So clearly the gain of the entire system is G1 times G2. That's fine. But I want to replace it with another system which has gain of G1 times G2, but an equivalent F. Okay. So what is the equivalent F? That is what I aspire for, because looks like noise factor is an important definition. And if I can reduce the definition of this multiple systems into one, that would be useful. Okay. So how do I go about doing figuring it out? We'll just use the same method that I have been using earlier, right? Club all the noise sources together and then equate input to output and so on. Okay. So, by the way, before I proceed, an important caveat or important distinction between marking my devices like this. It seems like they are uh, voltage control voltage sources because they have gain of G1, gain of G2, one driving the other. The gain is not getting affected just because I have put another, I've loaded the output of one with the other. That's not the case. This G1 and G2 includes loading, right? So G1 and G2, this is a loaded gain. These are not unloaded gain. These are loaded gain. Okay, so now what will I do? I will basically replace these F1, F2 and everything with these amps with their noise models. And what will be this, what will be the noise that I am going to write here? So if you go back to the definition, this noise is Nin times F minus 1, where Nin is a reference source, not the source that it is getting driven by, right? So this is some reference source. So let's say the reference source is an antenna, which has a 50 ohm load. And I call this NS, right? So this is NS, let's say. NS times F minus 1. Okay. Similarly, this one is, or F1 minus 1, this is NS times F2 minus 1. Okay. So what is the total N out? Total N out is NS times F minus 1, F1 minus 1 times G1 times G2 plus NS times F2 minus 1 times G2, right? So this should be equivalent to this guy, where I have NS F minus 1 and whatever I get at the output, right? What should I get at the output? You get NS F minus 1 times G1 times G2. So this should be equal. From there, I can find F, right? So essentially this becomes NS F minus 1 times G1 times G2. Sorry, I made a mistake. Total noise is this plus NS, right? So this is the contribution of only NS F minus 1, right? So something is coming out which is NS also, right? So this will be plus NS. Right, NS times G1, G2. Similarly, here also, I'm going to have yeah. Hold on, there is some mistake somewhere. Okay, so if I check the noise factor, what is the issue here? This is all right.
So we are standardizing with respect to some standard noise from.
Yeah,
but
yeah.
the input noise can be from any.
No, in this case, let's assume both, if you have to equate both these cases, I have to equate both these cases under the same condition. So the input noise has to be
Both these cases are some NN.
some
That is
NN.
not equal to standard.
That is not equal to standard. Yeah, I agree.
Okay.
Yeah, yeah. Yeah, yeah, right. So no, so what I'm trying to get at here is what is the, let me see if I have the derivation here. Okay. I don't know what the mistake I made. So what is the noise that I get here? This is NS plus NSF1 minus NS. So essentially NSF1. So the noise that I get here is NSF1 plus G1, right? So noise that I get here is NSF1 plus G1 times G2 plus NSF2 minus 1 times G2, right? So the part that got added up earlier, I made a mistake there, right? So here, so in this case, what is the total? In the first case, what is the total output? By definition, it will be, by definition of noise factor, it will be F times NS times G1, G2. Right? So that's the noise factor definition anyhow. Okay. So these two have to.
So it will be plus into yes, it's been even the stuff in dB, right?
We are in noise factor mode, right? So linear. G1, G2, everything is linear right now. If I write dB, I will write dBm.
How do you write from NSF1 to NSF1 plus G1? Should be multiplied.
Right. Correct. I'm not paying attention. NSF1, G1, G2. Does that make sense now? So this is NSF1, G1. This guy goes out as NSF1, G1, G2. This guy comes out as NSF2 minus 1 times G2.
That is the same thing that we did earlier. Took it down in F1 minus 1 and that.
Yeah. Correct. Yes. Yeah, fine. This is all right. So what I am trying to equate is what is the value of F for which these two are identical. Oh, I mean, till now, okay, right? So essentially, I'm saying F times NS times G1, G2 will be equal to F1 times NS times G1, G2 plus F2 minus 1 times NS times G2. So all the NS cancels. Basically, if I divide by NS G1, G2, I get F2 be equal to F1 plus F2 minus 1 divided by G1. Fine. So this is really similar to the cascaded noise SNR or input referred noise that we had gotten in the previous lecture, right? So what is this telling us? This is essentially telling us if you have two systems with G1, F1, gain G1, and gain G1 and noise factor F1 and gain G2 noise factor F2, you can basically replace this with a single system of gain G1, G2 and noise factor, which is F1, the first one, plus F2 minus 1 over the gain of the first stage, right? So again, just like before, you see that the noise factor of your entire system is heavily dependent on the noise factor of the first block. Because if your first block also gives you some gain, then the effect of noise factor of the second stage is hardly anything. Okay. So similarly, if I extend this to saying that if I have 3 of them and G1, F1, G2, F2, G3, F3, by induction, what do you think will be the total noise factor? Yeah, F2 minus 1 by G1. So the noise factor of this minus 1 gets divided by the gain of the preceding stage. Noise factor of this gets divided by the gain of all the stages preceding it, that is G1, G2. So the noise factors of the subsequent stages don't really play any part as long as they also give similar noise factors, right? So alternatively, another way of arguing is I can design the subsequent stages with probably not paying enough attention to noise as long as the previous stages give sufficient gain. Okay. Okay, fine. So we'll stop here. In the next class, we'll close the loop in the sense that you would understand why these two-port noise parameters are whatever we did at the beginning, right? Why these two-port noise parameters are important, and this is not only something to do some bunch of maths, right? So it has some design implications. Okay, thank you.